All right, welcome y'all. So today we're going to talk about thermochemistry in terms of bond enthalpy. So bond enthalpy is just another way for us to do thermochemical reactions and find out the enthalpy either produced or used when doing a thermochemical reaction. We've learned a couple ways, which is using things like Hess's law or using things like just the delta H of formation of each of the reactants and products and doing math that way. But we can also do it by literally looking at the energy it takes to form each bond. So this is actually my favorite way of doing it, and it involves us drawing things out. But before we even go into anything, I'm going to just start out with a little bit of background information. So to start us off, when we look at any bond, so maybe a carbon to a carbon bond, to produce our bond, we release energy. This is exothermic. And the opposite when we or when we break bonds, to break this bond, to break it, bond uses energy, and that's going to be endothermic. So using this idea, we can actually figure out our thermochemical equation for bond enthalpy, which is going to be, well, that's going to be too large of a stylus. The delta H of a reaction is going to be equal to the sum of the delta H of the bonds of reactants minus the sum of the delta H of the bonds of the products. So let's go ahead and just do some of these. If you watched our last video, you would have seen me do 3 equations in the end, and we used Hess's law to solve these 3 problems. We're going to return to the same problems with known delta H values and try and figure out whether we can get the same answer just looking at the overall reaction and calculating bond enthalpy. And it should work because if you remember, delta H is a state function. So all that matters is what is the energy in the beginning and what is the energy at the end. The way we figure it out doesn't matter as long as we get the right numbers. The last part you might be asking is, well, how do we know how much energy it takes to produce our bonds? Like that should be a known amount, and you're right, it is. You normally find this in the bond enthalpy and average bond enthalpy table at 298 Kelvin, and usually about 101 or 100 kilopascal standard temperature and pressure. This is a very easy table to read. All you do is you look at what's bonding, and you'll notice this is a single bond. So a bromine bonded to a bromine is 193. That's how much energy it takes to break it. A fluorine bonded to a bromine is 249, so it takes a bit more energy. You can get wild and do carbon and phosphorus, 264. You might notice that hydrogen has 436, one of the highest bond enthalpies. And sometimes we have multiple bonds. So in that case, we just have a couple listed here, double bonds, triple bonds, specifically bonds in benzene. Benzene makes the structure of a kind of, looks kind of like a lug nut, but it's basically any time when you have these 6 carbons and 3 double bonds. And this is actually going to be pretty important for us later on because we're going to use that bond in particular for our last problem. So with these values known, let's just jump into our first problem. We did this methyl propane 1-ol turning into methylpropane and water. And our original one got us an answer of 96 kilojoules per mole. We're going to use the same exact thing, but now we're going to look specifically at just the reaction. And we have to figure out how many of which types of bonds exist. And so the way we do this is we actually have to draw out the structures of each of these reactants and products and count the bonds. So I'm going to go ahead and do that right here. Now, some of this does take a little bit of chemical knowledge, and if you don't know it, we'll learn it later, or we'll learn it along the way. So these are organic molecules. They're a little bit harder to draw, but we'll give it a shot. Methylpropane 1-ol tells me, the prop tells me it's a carbon chain with an OH at the end because it's 1, so it's on the one end. This is our 1 carbon right here. So I'm going to go ahead and then put on the 2 carbon a methyl, which is just another carbon with some hydrogens. For the rest of these, I may not be drawing out the hydrogens just because that is extremely time consuming. But anyways, there's our methane propane 1-ol. If we look at it, we have hydrogen carbon bonds. We specifically have, let's count them out, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 of these. So we have 9 of these. We have carbon-carbon bonds. We have 1, 2, 3 carbon-carbon bonds. So I'm going to go ahead and write that here. Carbon-carbon. We have 3 of those. And we have a carbon, whoops. We have a carbon hydrogen, carbon oxygen single bond. We only have 1 of those. We have an oxygen hydrogen single bond. Again, we only have 1 of those. So we're going to add up all those values. Before we do, I'm just going to go ahead and draw the other things. So when this reacts, it forms what we have here, 2-methylpropene. Again, prop tells me it's a 3-carbon structure with a methyl group. And again, I'm not going to draw those hydrogens anymore. And this time it ends in -ene, which tells me that within the propane structure, one of them is a double bond. And so there's my carbon hydrogen bonds and an H2O plus H bonded to O bonded to H. So I'm going to look right here. I have O bond to H. I have 2 of those. I have carbon bonded to hydrogen. I have 1, 2, 3, 4, 5, 6, 7, 8 of those. And I have carbon bonded to carbon. I have 2 of those, and I have carbon double bonded to carbon. I have 1 of those. So now what I'm going to do is find out the values for each of these things. And I'm going to have to come back to my table. So I see that carbon bonded to carbon is going to be 346. Oops. 346. And that's our single bond carbon. 346. Oxygen bonded to hydrogen, 463. 463, and also over here, 463. I have carbon bonded to carbon double bond, 614. This one gets a little tedious. Carbon bonded to hydrogen, 414. 414. 414. Carbon bonded to carbon. I think I already pulled that one, 346. Carbon bonded to oxygen. I did not pull that one yet. Carbon bonded to oxygen, 358. So what I'm going to do is now take all these values. I'm going to add these up. I'm going to add these up, and I'm going to add these up, and then I'm going to take the sum of this minus the sum of these. So this is pretty much it. But before we even do that, I'm going to take a couple shortcuts. I noticed that I have 9 carbon hydrogen bonds here and 8 carbon hydrogen bonds here. And if I'm doing simple subtraction, I know that I can pretty much cancel out all 8 of these and all 9 of these. I'm left with 1. Because 9 times 414 minus 8 times 414 is just 414. Next, I have 3 carbon-carbon bonds and 2 carbon-carbon bonds. So I can cancel that out. Carbon-oxygen bonds are going to stay, and oxygen-hydrogen bonds. I have 1 over here, which will cancel out the 2 over here. My math has suddenly become a heck of a lot easier. I have on this side 614 plus 463, and all that is just 358 plus 346 plus 414. And so I'm just going to add those up and then all right, so I did a little math while the camera was paused, but I get 118 minus 1,118 minus 1,077, which gives me a net total of delta H being equal to 41 kilojoules per mole. Now, that is our answer. It unfortunately does not match the answer that we originally got. And I'll go through and just double check because I know another one of these turned out to even closer. But let me go back and check. When I check, I still got my original answer of 96 kilojoules per mole versus our new current answer, 41 kilojoules per mole. And the question might be, well, why the discrepancy? It's pretty close. It's within the same order of magnitude, but it's understandable that there would be a discrepancy. When we take bond enthalpies, one thing you might notice is our table says average bond enthalpies, which tells you that these aren't exact values, much like our atomic masses aren't atomic masses or average atomic masses of different isotopes. These are the average bond enthalpies of a substance. If I look at the OH bond in hydrogen peroxide, or I look at the OH bond in water, this bond right here and this bond right here are very different. They actually have different bond enthalpies overall because in one case, the oxygen is only bonded to another hydrogen, while in the other case, it's bonded to another oxygen. These elements have different electronegativities and pull on these electrons, creating different dipoles within these molecules. So in actuality, our problem over here, these bond enthalpies aren't exactly the same. The OH bond that we see here is different than the OH bond that we see here. And they can create quite a big range of discrepancies. Overall, though, it's fine. If you're called to use average bond enthalpy, then it's understood that you won't have exact values. In a problem where they specifically set you up for Hess's law, use Hess's law. But honestly, I have more fun with bond enthalpy. So moving on, we'll try the next problem. This is the one with butane to all, and it's hydration hydration of butene. So let's go ahead and try and figure this one out. If I look at butene, C4H8, I know that it is but, so we start with a 4-carbon chain. On the second carbon, I have my ene, that's my double bond, and then I can just fill in the hydrogens. We'll get 1 hydrogen on each of these. Something we'll get to way in the future is this is our cis structure, as both our hydrogens are coming off from the same point. That gets into chirality. We'll get to it later, but I just want to point that out to you. We add that to our water. And in the end, we get butane to O. So that's butane, our 4-carbon structure, carbon, 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 carbon. And on the second carbon, we have our OH. Other than that, just fill in with our hydrogens. So let's go ahead and count. We have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8 carbon hydrogens. Carbon, hydrogen, we have 8. We also have carbon, carbon, we have 2. And we have carbon, double bond carbon, we have 1. Our H2O has HO bonds, we have 2. And then lastly, we have our carbon hydrogen bonds in our product, which is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. We have our carbon-carbon bonds, which is going to be 3. And we have our carbon-oxygen bond, which is going to be 1. And our oxygen-hydrogen bond, which is going to be 1. And again, I'm just going to do some simple math, which is where if I have 8 carbon hydrogens on this side and 9 on this side, I know I just have 1. If I have 2 carbon carbons on this side, and I have 3 carbon carbons on this side, it's just going to be 1. if I have two hydrogen oxygens on this side and one hydrogen oxygen, it's just going to be one. And so now when I add these up, I can get whatever my answer is going to be. So I will pause it, fill in the numbers, and do the math. You do that as well, and let's see if we get the same answer. When I look those values up, these are my values that I'm going to plug into my calculator. And I realized this actually is the same exact math of the problem, but surprise, surprise. And so this time, instead of 111A minus 1077, it's the inverse. So this is going to be minus 41 kilojoules per mole, which turns out is a heck of a lot closer to our minus 44. Still all right. And we're still going to have that variation once again because these are average bond enthalpies, not the true bond enthalpy. All right, our last one's a bit harder. On this one, I'm going to draw the structures because it may be almost impossible for you to draw them without the knowledge yet. And after I've drawn them, I will give you a moment to pause, and I want you to try and do this on your own, find out how many bonds are of each, and see if you can come up with an answer, and then we'll do it together. So on this last one, we're talking about quinone, C6H4O2, and hydroquinone, C6H4OH2 with hydrogen peroxide, and we also have some liquid water thrown into the mix. So let me go ahead and draw the structures. Firstly, we have hydroquinone, which is going to be C6H4 in a circular pattern. And I mentioned before we were going to have that benzene ring structure, and this is actually the case where we do. Those triple bonds don't really matter too much where you put them. But these carbons do actually have that benzene structure, and therefore these would be carbon bonds that look like that. So you're going to be using those bond enthalpies, which means you're going to have to use each individual one. Now plus hydrogen peroxide, that's just, whoops, OOH, react to form quinone, which is a little bit harder. This one has an almost similar structure, but you'll notice it actually has the double bonds opposite and parallel to each other. And then we have double bonds to two oxygens. And lastly, water. We all know the structure by now, H2O. So at this point, I want you to go ahead and pause the video to count out each one of the individual bonds, and then add those up if you can, and see if we can get some value that somewhat resembles negative 161 kilojoules per mole, the answer we got before by using Hess's law. So I'd say pause your video now. All right, I hope your work was fruitful. So what we have here is I've just counted up the individual bonds. I haven't put any bond energies to them because I'm going to go ahead and try and cancel some of these values out first if I can. So I see on the right side, I have two hydrogen oxygen bonds, two hydrogen oxygen bonds, and two hydrogen oxygen bonds. So we can honestly fully cancel out water on this side and fully cancel out the hydrogen oxygen bonds of either hydroquinone or hydrogen peroxide. We also have carbon double bond oxygen and so forth, but no other things cancel out. So we're just going to go ahead and have to do the math for these. So I'm once again going to pause so I can grab the value. All right, with these numbers in place, I'm going to set up this problem the way it should be properly set up now that we have multiples of each individual bonds. So I'm going to go ahead and set up some brackets. I'm going to do 6 times 507 plus 2 times 358 plus 2 times 414. I'm going to add all that to 144. And then I'm going to subtract 346. Oh, sorry. I'm going to subtract 4 times 346 plus 2 times 614 plus 2 times 804. And so all you have to do is put these values in your calculator and solve this out. After doing the math, I get 4,730 minus 4,220, which in total gives me an answer of 510 kilojoules per mole. Now, unfortunately, that is not even close. So, honestly, I probably did something wrong. Or this method just doesn't always work properly. Sometimes we have to use this method, sometimes we have to use Hess's law. I'd say overall go with what they show you. However, oh, actually, I'm going to remedy myself right here. I made a mistake, and you may have caught it earlier. This whole problem isn't one H2O, it is two H2Os, which means that our original one had OH, which turns out that's a whole discrepancy of another 828. So in our original math, we didn't just have one set of OHs, we had OH2 again. So what we should have done is cross that out, and now we can take out from our equation this 2 times 414. That isn't even there. So I'm going to go ahead and actually redo my math and see what happens. So give me just a all right, so doing this math over again, turns out our products actually have an original bond enthalpy of 3902 that they are contributing when we factor out all the things that cancel out, which means our new delta H for this equation is negative 318 kilojoules per mole. Now, I'm much more satisfied with this. For the one thing, it's negative, which shows that this reaction is exothermic, which is how it's supposed to be. This is an exothermic reaction. Second, it's only about double of what our original one was, minus 161, which can easily be attributed by the fact that the bond enthalpies of our hydrogen-oxygen versus our hydrogen-oxygen of water and hydrogen peroxide, or water and the alcohol groups, shown here, shown here and here, versus our water ones, should actually be different. In fact, we should have a little bit more energy on these two down here, making 3902 probably closer to around 4,000, maybe just around 4,000, and this value should be a little less, maybe about 4,160, which means our answer in total would be minus 161. With that said, it's all right. We're using bond enthalpy. We're bound to be off, but I hope this helps. And yeah, have a great day.